Hi, how's it going, everybody? We're starting Chapter 7 now, and in Chapter 7 we're going to be focusing on right triangles, and whenever you talk about right triangles, a great place to start is with talking about Pythagorean Theorem. Now, Pythagorean Theorem is something we've used throughout the school year already, so you're familiar with an equation associated with it. What we're going to be focusing on is, again, how do you use Pythagorean Theorem, but we're going to look at a couple of applications of Pythagorean Theorem within this section. In this video, we're specifically going to apply it to finding areas of right triangles and isosceles triangles. In the next video, we're going to look at something called Pythagorean triples. And so those are each things that you need to be familiar with in terms of Pythagorean theorem. All right, now, you're going to use Pythagorean theorem to find the missing side lengths of a right triangle, but then also to find areas of right and isosceles triangles. Pythagorean theorem. I've challenged my kids throughout the years, whenever we get to this section of the geometry book, to tell me what the Pythagorean theorem is. And it is a very rare occasion when somebody can actually tell me what the Pythagorean theorem is, because most people just give an equation. And that equation, a squared plus b squared equals c squared, is certainly associated with the Pythagorean theorem. In fact, I'll write it down here. But in and of itself, that equation is not the Pythagorean theorem. Now, I'll get to the theorem in a moment. You see the picture of this guy right here. This is a guy whose name is Pythagoras. He is the guy who is, well, he and his followers are kind of credited, maybe falsely, who knows, but kind of credited with coming up with the first proof of the Pythagorean theorem. Although there's evidence that there were Babylonians, for instance, that were using Pythagorean theorem from a long time before Pythagoras was. But Pythagoras is a pretty old guy. He is around between 570 BC and 495 BC. Really a philosopher, founded a religious movement that was based on mathematics heavily called Pythagoreanism. Something worth looking into if you're interested in math history whatsoever. Perfect for you. But back to what I said earlier about the Pythagorean theorem not really being a squared plus b squared plus c squared, or equals c squared. All the theorems in our textbook this year, if you haven't noticed, come in the form of conditional statements. And so here's what I need to ask you then. What is the condition under which you would apply the equation a squared plus b squared is equal to c squared? And I hope that you can tell me that that condition is whenever you have a right triangle, such as what I'm showing you right here. Okay, so here is the Pythagorean theorem. If a triangle is a right triangle, then, so an if-then statement. Now listen to the phrasing here, because I'm not going to write an equation. If a triangle is a right triangle, then the sum of the squares of its legs equals the square of its hypotenuse. All right, so that's actually the Pythagorean theorem. But what you're going to remember, generally speaking, is the equation associated with it, and that's fine, as long as you understand what the A, B, and C represent. Now remember, within a right triangle you have two legs and you've got a hypotenuse, and the hypotenuse is always the one that is opposite of the right angle. And always when you're using Pythagorean theorem, you want to make sure that the hypotenuse corresponds with the C that's right there. And then the other two sides of the right triangle, the ones that form or include the right angle, these sides are called the legs of the right triangle. So the sum of the squares of the legs, square of this leg plus the square of this leg, equals the square of the length of the hypotenuse, so equals c squared. That's Pythagorean theorem. You knew that equation already. How do you use it? Well, here's what I want you to do. First, I want you to find the length of the hypotenuse. Now this may or may not be new for you. One of the things I want to include in this section is how you leave answers in simplest radical form. All right. Well, let's get into the Pythagorean theorem part of it first. So you can see that this is a right triangle indeed, and so that equation c squared equals a squared plus b squared, or a squared plus b squared equals c squared, whichever way you want to write it, does apply. And first thing you need to notice is which sides of the triangle would you consider to be your A, B, and C. And the important part is that you let your hypotenuse be C, and you can see that this is the hypotenuse because there's the right angle, correct? And then it doesn't matter which leg is A or which leg is B, does it? All right, so in this case, if we're writing C squared equals A squared plus B squared, well, let's substitute the values that are given. That's going to be M squared is equal to 10 squared plus 8 squared. All right, nothing special about this part. Just make sure you follow order of operations. So square the length of each leg first and then add them together. You get 100 plus 64. So M squared is equal to 164. And then, of course, if you know M squared equals 164, M is going to be equal to the square root of 164. Now, I'd like you to be in the habit of leaving your answer as an exact value. The square root of 164 would not be an integer, it would be an irrational number. I don't want to approximate it, so I'm not going to change it to a decimal. I'm going to leave it in radical form. But I'd also like you to now to be focused on what is simplest radical form. And the way you find the simplest radical form, this is my strategy anyway, is you try to find a perfect square that's a factor of your radicand. And preferably you find the largest perfect square that you can that's a factor of the radicand. Now, perfect squares, of course, being 4, 9, 16, 25, 36, 49, 2 squared, 3 squared, 4 squared, all those things. Well, in this case, I think you can see that 4 would be a factor of 164, and so that's my perfect square factor. And here's what I'm going to do with that. I'm going to rewrite this radical as a product of the square root of 4 and the square root of 41. Now, 4 times 41 is 164. That's where the 41 and the 4 came from. And then every factor here that is a perfect square, you can take the square root of. You can take the square root of 4. That just becomes 2. You cannot take the square root of 41, and so you leave it there. Now, you'd also want to see, are there any perfect squares that are factors of 41? 41 is a prime number, so there's, of course, not going to be any factors of 41 that are going to be relevant to us. So there's us finding the length of the hypotenuse. Now, let's go to an example where we're going to be finding the length of an unknown leg. And we want to leave our answer in simplest radical form again. Well, before we really do much with this, other than observe that the missing length is a leg, because here's the hypotenuse, since the right angle is right there, is I want us to think about a way of rearranging the Pythagorean theorem equation. All right, you're used to saying that c squared is equal to a squared plus b squared, and that's great whenever, well, it's great at all times, but whenever your unknown value is a hypotenuse, that's great because you've got the hypotenuse on one side of the equation by itself. But let's say, for instance, in this problem, all right, that's going to be our c, say the 10 is our a, and the q is our b. If we're trying to find the value of b, it would be nice to have the b's by themselves in this equation. And that's very simply accomplished by subtracting a squared from both sides of the equation. Wouldn't b squared be equal to c squared minus a squared? My point being then that the square of the length of either leg equals the difference in the squares of the hypotenuse and the length of the other leg. So b squared equals c squared minus a squared. You can also say that a squared equals c squared minus b squared. Hopefully that makes a little bit of sense. Helps with the math a little bit, saves in 1 or 2 algebra steps anyway. So using that idea, we can then say that q squared, because that's our b, is equal to 20 squared minus 10 squared so then q squared is equal to 400 minus 100, and then q squared is equal to 300. So q would be equal to the square root of 300. That's its exact value. But let's give it in the simplest form that we can, meaning we're going to simplify the radical. Now again, we want to find a perfect square that's a factor of the radicand 300. I hope you can see that 100 is a perfect square and that it is a factor of 300. We can make that the square root of 100 times the square root of 3, and that will give us then 10, because that's the square root of 100, times the square root of 3. Can't find any perfect squares that are factors of 3, so we can't simplify that radical anymore. Good so far, I hope? All right, now let's go on to a couple of applications of Pythagorean theorem. I said we're going to be using in this video strategies to find areas of right triangles and of finding the areas of isosceles triangles. All right, and we're going to find the area of this triangle that you see right there, which happens to be a right triangle. The area formula for a triangle is still going to be the good old-fashioned 1/2 times base times height. But here's really what I want to tell you in regards to the area of a right triangle. Most of the time, you want to pick two specific sides for the base and the height. You can let any side of this triangle be the base and any side be the height. It's not like the bottom side has to be the base every time, like you might think. The only condition is that the base and the height have to be perpendicular to one another. And in a right triangle, that's great because the legs are perpendicular to one another. And so what I would suggest is using one leg for your base and use another leg for the height, all right, rather than the hypotenuse. There are times where you will use the hypotenuse for the base, but generally speaking, use one leg for the base, the other leg for the height. So we could say then, for instance, that this would be our base and this would be our height. That would work out nicely, except that we don't know this measurement right here. So let's say we call that x. Well, we're going to use Pythagorean theorem to find that. Now that unknown measure there is one of the legs, and we can then say that x squared is equal to the difference between the hypotenuse squared and the other leg squared. So it's equal to 6 squared minus 4 squared. And that's going to be 36 minus 16. X squared then would be the square root of 20. And then if we simplify that, that becomes x is the square root, x squared is equal to 20, so x is the square root of 20. X then would be equal to the square root of 4 times the square root of 5, or 2 square root of 5. All right, now for the area, we now have a measurement for our base. We know that's 2 square root of 5, and our height, we're calling that 4. So let's plug those into the area formula. 1/2 times 2 square root of 5 times 4. Now multiplication is commutative, right? I've got 3 factors in this product, and I can multiply them in any order I want to. And whatever I'm multiplying by 1/2, I prefer to multiply 1/2 by an even number if I can. We got 2 ways of doing that here. In this case, let's just go ahead and multiply 1/2 times 2 square root of 5. And 1/2 times 2 square root of 5 just gives you 1 square root of 5. You don't have to write this 1 right there. You can just leave it as a square root of 5. And then the square root of 5 times 4, well, you can't multiply, if you're trying to leave your answer as an exact value anyway, a radical with a non-radical. And so what we're just going to do is put that 4 in front of the radical, and we're going to say the area is 4 square root of 5. And then our units will be square meters because the side lengths were measured in meters. There you go. So always use, 95% of the time or more, use one leg for the base and one leg for the height when you're working with a right triangle. All right, last example here. We're going to find the area of an isosceles triangle using Pythagorean theorem to aid us here. Now we're still using area equals 1/2 times base times height. And once again, I'm going to tell you that you don't have to use the bottom side of a triangle as the base. And I drew this triangle so that you wouldn't. In an isosceles triangle, the easiest thing to do is to use, you've got 2 legs in an isosceles triangle, right? And then you typically will call the non-congruent side in an isosceles triangle the base. And I would always use that for the base. It's called the base almost for that reason. So we're going to use this for the base. Okay, and here's how we're going to find the height. And the height has to always be perpendicular to the base. And neither one of these sides is perpendicular to this, is it? So we're going to draw an altitude then. All right, from the opposite vertex, we'll draw a perpendicular line. Yeah, the software isn't letting me make too great of a perpendicular line, but I'll label it as perpendicular anyway. All right, so pretend with me for a moment that's actually a right angle. Sorry about that. And what's going to happen then is that's going to create a pair of right triangles, okay? Now, that distance that we drew is going to be the height, and in order to find the height, here's the way we're going to go about that. We're going to say, because it's true, Every time you draw the altitude to the base of an isosceles triangle, it's going to bisect the base. All right, you could use HL, for instance, to prove that these two triangles here are congruent to one another, which kind of proves that this is a bisector. All right, there's other ways of doing that. We can say this is 10 and 10 since that whole thing is 20. And then, if you'll just focus on one of the right triangles, say this one right here, you can find out the height of the isosceles triangle. Okay, so that height happens to be one of the two legs. See, it's one of the sides that forms the right angle. So we can say that h squared here is equal to the hypotenuse squared minus a leg squared. That's equal to 676 minus 100. And that's equal, h squared then was 576. And 576 turns out to be a perfect square. The square root of 576 is exactly 24. So we actually got one nice number here. We know the height here is going to be 24 millimeters. And now we can just go and plug in that height along with the base that we already knew. Remember, 20 is the base. That's the entire base right there. Plug that into our area formula. So area is going to be 1/2 times 20 times 24. Then multiply the 1/2 by either one of these numbers. Let's just do half of 20. That's 10. And then 10 times 24. 240 square millimeters. Well, that's an ugly 240. 240 square millimeters is going to be the area of that isosceles triangle. All right, so with an isosceles triangle, draw the altitude to the base to make two right triangles where one leg of the isosceles triangle is a hypotenuse for the right triangle. And then find the area that way. Guys, thanks for watching. Appreciate your attention. Good luck with these skills. See you next video.